now we have some basic knowledge on tensors. Let's go ahead and create them with TensorFlow. So first things first, we would import TensorFlow as TF, and then you should note that because we're using Colab, we do not need to install TensorFlow before making use of it. All we need to do here is just import and we're good to go. Now, first thing we're going to do is we're going to have our tensor, which we'll call tensor 0D. And the way we're going to create this tensor is by calling on the constant method. So we have TensorFlow's constant method, and then we specify, for example, that we want this to be, let's say, 4. So that's it. That's how we create a zero-dimensional tensor. You could see here from the documentation that this constant method takes in a value, takes in a data type, takes in a shape, and a name. But for now, we pass in only this value right here, and then we could go ahead and print this. So let's have tensor 0D, run that. You could see right here, we've had this tensor, which has value 4. It has no shape, and it's of type int 32. With this, we could go ahead and build out our tensor 1D. Tensor 1D, we have, as usual, our constant method, but this time around, because it's 1D, we're going to have a list. We're going to take this list we had here, 2, 0, -3, and then put in this now right here, we have 2, 0, and -3. Now let's print this out. We have tensor 1D, and there we go. You see, we have the value, which is this 1D or this list. We could see shape right here, and then the data type. Now let's modify this and say we have 8 and let's say 90. Let's run this now and check out its shape. You see here, this is our new list, or this is our new tensor, and then you see now it's 5 because we have 5 elements in here. But again, this is still an integer. So let's add this here, change this to a float, and then see what we have. See here, now this is a float. So it's still our inputs, but this time around floats. Same shape, but the data type changes from int to float. Let's get back to integer, and then we move now to the 2D tensor. So we've looked at 0D, 1D to create a 2D tensor. It's going to be quite as simple as we've done with the 0D and 1D. So here we have 2D, and then we have, as usual, our constant, and then let's open up this square brackets. So we have the square brackets right here opened up, and then we would have this 2D tensor we had seen already. So let's have this right here. We have 1, 2, 0. We put a comma to move to the next row or to the next line. We have 3, 5, -1. Then we have 1, 5, 6. And then we have 2, 3, 8. Okay, so as you could see here, we have this 1D tensors which we stack and which will form our 2D tensor. Now, as usual, we have our constant method which takes in this value. And you should also take note of the fact that we have this outside of this stacked 1D tensors. Now we have this. Let's go ahead and print out tensor 2D. We have tensor 2D, and there we go. As you could see, we have our 2D tensor. That's it. We have the shape 4×3, which is what's expected, and then the data type is int32. From here, we move on to the 3D tensor, which is essentially made of this 2D tensors which have been stacked together. So let's go ahead and see how to create this with TensorFlow. We'll start by putting together those 2D tensors. We had 1, 2, 0, 3, 5, -1. So that's it. 3, 5, -1. And then we have all those remaining 2D tensors. So let's get here. We have tensor 3D. It's a constant. We have our square bracket here, and then we simply copy this, and then paste this in here. Now let's print this out and see what we get. So here we have Tensor 3D. As you could see, we're getting an error, and this comes from the fact that we omitted commas. Now, if you look at this, you'll see that between 1D and another 1D to form this 2D, there is a comma. And so this means that between this 2D and this other 2D, there should be a comma. So let's have this comma here. Let's have this comma. Let's have this comma and this comma. Okay, so let's run that again and see what we get. As you could see, we have this our 3D output of shape 4x2x3, and that's exactly what we expect to get. Data type int 32. Now, before we move on, we should note that we could also do, let's have this here. We could also do Tensor 3D shape to obtain this tensor shape. So you see that we have that right there. We could replace this 0. We could have 1. See, that's 0, that's 1, that's 2. There we go. Let's have 1. That's 1. That's it. Okay, and also we could also have here, let's say 3. We could do ndim, and this gives us a value of 3, showing us that our tensor is a 3D tensor. At this point, we've looked at 0D, 1D, 2D, and even the 3D tensor. Let's go ahead and check out a 4D tensor. But to construct a 4D tensor, we need several 3D tensors. So let's have this here. We have this 3D. Well, we saw this already. This is this 3D. And then we move to this other one right here, or there's two others. We have this other 3D and this other 3D. And then now if we stack these 3Ds up, what we'll obtain would be a 4D tensor. See, we have this one, we add this other, and we have this other. So now we have here a 4-dimensional tensor, which is made of three-dimensional tensors. Now you should know that this could be 2, this could be 4, this could be whatever number. So if we consider only this 2, then we're talking about 2 3-dimensional tensors. But what's so important to note here is the fact that once you stack several 3D tensors, you create a 4D tensor. Now at this point, you could take it as an exercise to create your own 4D tensor. So you could pause the video, but we're going to go ahead and show you how to create this. First things first, we're going to take up our 3D here. We have this 3D tensor. Let's just copy this. There we go. We paste this out here. Let's repeat that operation. Copy and paste again. But now let's modify some values. So let's say we have 13, 26. Let's just randomly modify this. 23. So it's now this other 3D is different from the other one. Say 30. Okay, now let's copy this again and then paste out here. So we have the 3D tensors. Let's say this is 10. Let's just add zeros. We have here 20, 3, 2, 4, and say 2. Okay, so now we have our 3D tensors. We have this one, we have this other one, and then we have this other one. Now to create our 4D tensor, as usual, we call on our constant method. So we have 4D, we have the constant, and as usual we have our square brackets, which will open up, and then now we'll just simply take this, copy all this to the end, cut this from here, and then paste this out here. Okay, so we see we have 3 of this 3D tensors. Now remember last time when you were separating 2 3D tensors, or between the 3D tensors, we need to have a comma. So here we're gonna have this comma, and then here we're gonna have this comma, and here we have a comma. Okay, so that's it. So let's run this, or let's print this out and then see what we get. So here we have print tensor 4D. There we go. You could see from here we have our 4D tensor. You see its shape 3 by 4 by 2 by 3. And this is because our 4D tensor is made of let's take this off. It's made of 1, 2, 3 3D tensors. So that's why we have 3. And then for each and every one of this, we have 4. That's 1, 2, 3, 4 2D tensors. So here we have 4. And for every 2D tensor, we have 1, 2. That's 2 rows. And 1, 2, 3. That's 3 columns. And that's now exactly what we have here. So we still have the same data type. We have values, which we could have here. And that's it. If we get back here, we'll see that we have different data types which we could use. So instead of just this default int, we could have tf float, say 32, and you'll notice that the outputs, as we had seen already, should have these decimals, since we're now dealing with floats. Now the float we have in here is of type float 32, or specifically the float 32, meaning that the precision value here is 32. Now if you reduce this, you'll see that you would actually have the same output, but the difference is that less memory is allocated for storing this tensor as compared to maybe even, let's say, the 64, that's float 64. And so in certain contexts where we have the memory constraint, we would want to use the lower precision tensors. In the documentation, you could have all the different data types which are supported in TensorFlow. So here we have quantized data types. And talking about quantization, we're going to treat this in subsequent sections. And so don't bother for now if you don't really master this. Here we have the brain floating point. Here we have the Boolean. Here we have complex in its 128 and 64-bit versions. Here we have the double, which in fact means the double precision floating point. Now this is double because the float 32 is a single precision. So here we have single, the float 16 is half prediction or precision, and then the double is double precision. Here we have the ints and their different versions or the different precisions. We have the quantized ints. We have resource, we have string, we have unsigned int, and then we have variant. Getting back to the code, if for example here we had this float, let's just add this decimal, so we suppose that this is a float, and then now we do int, let's say int 64, we run that, you would see that we would obtain an error. So let's have this here. What do we see? We told that we cannot convert this tensor to eager tensor of the data type int 64. But now if we use the cast method, if we do TensorFlow cast, and then here, or rather, let's take this back. Let's have our TensorFlow or our Tensor 1D, and then let's take this off, or let's just have this float 64. There we go, or let's say float 32, and then let's say we define some casted tensor 1D, and then this casted tensor 1D is simply going to be the casted version of this or 1D tensor. So here we have tensor 1D, and then we specify the data type, and then we say we want this to be in 16, for example. So here we're going to print out the tensor 1D, and we're also going to print out the casted tensor 1D. We get in this error. We should have had tf dot, so let's have this here. There we go. And then let's look at what we have as output. As you could see, thanks to the casting operation, we are able to get from this float to this integer tensor. And so this tells us that instead of coming right here and saying, for example, int 16, or let's say int 32, it's preferable to make use of the cast method. That said, let's say, for example, instead of having this, instead of casting this into an integer, we want to cast this into a boolean. So let's run this. You see here that we get all true except for this one here, which is false, and that's simply because this is a 0. So it looks like what the casting method does is, for all the values which are different from 0, they're true, but values equal 0 equal false. We could also go ahead and create our own boolean. So let's say we have tensor bool. Let's call this tensor bool, and then we have this list made of this tensor. So we could have true, true, false, true, true, false. Okay, so let's print out tensor bool and see what we get. As you could see here, we have our output tensor of shape 3, and here is values. You can see the data type bool right here. Now another data type which we could look at is the string. So let's say we want to have tensor string. There we go. Let's say we want to have hello world. Let's print this out, tensor string. There we go. We have our tensor. We could also put this in a list because right now this is a 0-dimensional tensor. So let's put this in a list, and hello world, hi, and we'll close that. And now we have this 1D tensor of shape 2, which is a string. From here, we would also look at how to create or how to convert a NumPy array into a tensor. So let's call this NP array. First of all, we'll start by importing NumPy as NP. We could just do that right here. Import NumPy as NP. There we go. And then we have NP array. And let's say we have NP array, and then let's take in this here. Let's say 1, 2, 3, or 1, 2, 4. There we go. Print this out. We have NP array right here. Now we could make use of this TensorFlow convert to tensor method. So let's say we have your converted tensor, and we have convert to tensor, which essentially takes in our NumPy array. Now let's have this and then print out the converted tensor. With that, getting back to the documentation, we could look at a couple of other methods, like the I method. Here we have this I method right here. As usual, we have the well described method in the documentation, which comes with this short phrase explaining how it works. It comes with this different arguments and also even some examples. So getting back here, we told that this I method permits us construct an identity matrix or a batch of matrices. So now we have this definition. We could simply copy this out and then get back to the code right here, paste this out, and let's say we call this I tensor, and for now we have this number of columns which is known, the batch shape known, data type float 32, name known. Now let's say we want to have 3 rows. So we have number of rows which is equal 3. Now in this case, we'll print this out so we see the kind of output we get. Here we have I tensor, and there we go. As you could see, we have this identity matrix where all the values of the matrix are 0 except for those of the leading diagonal. Let's show clearly this leading diagonal right here. Here we have our matrix, which is this, and then we have this element of the leading diagonal which is equal 1. Now you should note that you could say, for example, let's say 3 times this, and you should have all the elements of the leading diagonal to be equal 3 and the others 0. So in this case, we now have something like this. So you see all this 3 while the rest 0. Now let's get back. Let's take this off. Here we have our I tensor, and then we see that we could specify the number of columns. Now here, or previously where this was set to none, we had a square matrix. That is, when you define the number of rows to be 3, the number of columns automatically takes up the value of 3. So we have a 3 by 3 matrix, and obviously the type here is float 32. We could modify this and say, for example, 16. Run that. Let's try out bool after this. There we go. We have float 16. Let's try out bool. You see everywhere is false, 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 except for the leading diagonal, which has true. Now getting back, let's say here we have 5, and then now number of columns, let's set this to 3. You see right here, this is the output we get. Now it acts like we have a 5 by 5 matrix. So we suppose we had a 5 by 5 matrix where this would be 0, 0, this would have been 0, 0, this would have been 0, 0, this would have been 1 if this was 5 by 5, 0, and then here 0, 1. So this is what we would have had if we did not, if we let this to be known, that is number of rows equal number of columns. But now that we've set number of columns to be 3, this part has been cut off. And so this is what we're left with now. With that said, let's go ahead and take this back to none, and then let's set a batch shape. So let's say this is 3. Run that. As you could see, because we set this batch shape to be 3, here we have this output, which is 3 by 5 by 5. Well, let's change this to 2. So you could see that this actually is responsible for deciding on what number of batches we have right here. So here we have 2 by 5 by 5. So essentially saying that you want to have this batch shape to be 2 like this means you want 2 5 by 5 matrices which are identity matrices, that is which have their values all zeros except for those of the leading diagonal which are equal 1. And so we see how we could create this 3D matrix or this 3D tensor from the I method. Now we could go ahead and say, for example, we want 4 here. Let's run this and see what we get. We should get 2 by 4, 2 by 4 by 5 by 5. See here we have 2 by 4 by 5 by 5. And that's it for the I method. We move on to the next method, the fill method. Here we have a method as defined here in the documentation, which creates a tensor filled with a scalar value. So here we have this fill method, which we're going to copy. But before testing out the code, you could see here from this example that with this fill method, we have this tensor which takes which has shape 2 by 3 and which has value 9 on all its different positions. So let's get back here. Paste this out. Let's call this fill tensor, and let's say this dimensions, let's say we have 3 by 4, and then let's say we want to have the value let's say 5. Okay, so let's print this out and see what we get. Fill tensor, and there we go. That's the output we get. Now let's have this one, for example. Run that. See, we're able to create this 3D tensor where all the values or all the elements in each position takes the value 5. From here, we'll go on to the once method, and it should be noted that this once method is quite similar to the fill method in the sense that this creates a tensor just like with the fill method, but the only difference is that here all the elements are set to 1. So you notice that here in this definition, we do not have this value argument. Right here we had a value which we pass, but with a once there is no value because the value by default is 1. So let's have this here and then paste out right here. See, we have this once, so we'll call this once tensor. There we go. We specify the shape, let's say 5 by 3, and then we print that out. So here we have once tensor. And there we go. We have this output matrix which is made of 5 rows, 1 2 3 4 5, and 3 columns, 1 2 3, where all the elements of this tensor take up the value 1. Now you could obviously do this to have or to obtain a 3D tensor. So that's the output we get. See, it's 5 by 3 by 2. From here we'll look at the ones like, and what this one does is it creates a tensor of all ones that has the same shape as the input. So what this means is, if you have an input like this one, let's say we have 12, let's not make that 1, 12 1 3, and then 5 7 2. This is actually a 2 by 3 matrix. Let's change this. So you see that this is 2. So we have the shape. The shape is 2 by 3. So its shape is 2 by 3. Now, if this is the input here, if this is the input into our once like method, what we'll get as output will be a matrix or tensor with this same shape, that is with shape 2 by 3. So our output is going to be having a shape 2 by 3, meaning that we're going to have 2 rows and then 1 2 3 columns. But the output, or rather the values we're going to insert here, will be all ones. So now we're going to have 1 1 1 1 1 1. So hence the name ones like. So this like is actually for the shape of this. So you're imitating the input with respect to its shape. Now getting back here, you see we had this field tensor, which is a 1 by 3 by 4 tensor. So let's have this right here. Let's say we want to have ones like tensor. There we go, tf ones like, and then we have field tensor. There we go. Okay, so let's print out this ones like tensor. Now before printing, let's try to obtain the output. So here we know that this is field tensor. The shape is 1 by 3 by 4. So it means that we should have an output of shape 1 by 3 by 4 where all these values are ones. So let's run that and make sure that that's the output we have. There we go. See, it's 1 by 3 by 4, and we have all ones. From here we move to the zeros method. So it's quite similar to the ones here. Just like with the ones, we have all elements set to a given value. With the ones, all the elements were set to 1. With the zeros, all elements are set to 0. So that's essentially it. Now let's just modify the code a little right here. So this was ones tensor. Let's change the shape, this 3 by 2, and then instead of ones here, let's say zeros. Here we have zeros, and let's call this, well, let's say this is, let's just copy this out and put out separately. So here we have this, we paste that out here. We have zeros, and here we have zeros, fine, and here we have zeros. Okay, so let's run that, and there we go. We should have this here. So you see it's 3 by 2, 3 rows, 2 columns. That's fine, and all values are zeros. If you were ones, then you have all values ones. And for the ones or the zeros like is similar to the ones like, so you could take that as a simple exercise. We then move forward. We have this shape method right here, where we told that this returns a tensor. Take note of that. It returns a tensor containing the shape of the input tensor. So as we had seen before, we could obtain the shape of a tensor by simply making use of that tensor's name dot shape. Now if we want to have an output, like in our case now we want to have this output tensor which contains the shape of our tensor, then we could make use of this shape method from TensorFlow. So you see here we have the same 4 by 2 by 3, but this is now in this list and then we have its shape, and we also have its data type. Obviously it's made of integers, so we shouldn't expect to have a float data type right here. Another method which we could make use of is the rank method, which simply returns the rank of a tensor. So it takes in the input and then returns its rank. You have a simple example right here where we have this 3D tensor T, and then when you call on the rank method, you see that we obtain the output, which is 3. So let's put that out here. Let's just paste it out here and test that quickly. There we go. As you could see, because the output is a 0-dimensional tensor, the shape, it actually has no shape, but you could see its value right here. That's 3. Now if you take out this and take out this and then take out this other part here, there we go. We run this again. We should have a rank of 2 this time around. That's fine. You see here the rank is 2. We now move to the size here, the size method, which returns the size of a tensor. So you put in an input in the size method, and it gives you the size of the tensor. We have, as usual, on the example here, which we could copy. But before running that, we could read this note here, where we told this returns a 0D tensor representing the number of elements in the input of type output type. This is the output type here, which by default is int 32. So let's get back here and paste this out and check out the size. As you could see here, we have this size of 12, and that's because we have 12 different positions or 12 different elements in our tensor. Now let's take this off again. Take this off. Take this off. There we go. Let's run that. We should have 6. So that's it. You see, we have 6. And yeah, we could also specify this the type. Let's say float 32. We get an error here. Got an unexpected keyword argument D type. Now getting back here, you see this is actually out type, not D type. So let's get back here, and then we have out type. So we have out type. There we go. Run that, and as you could see right now, we have a float instead of an int. The next step we'll take is creating our own random tensors, and that is essentially creating tensors which take up random values. Now in the case of TensorFlow random normal, our output values are going to be from, or are going to be drawn from, a normal distribution, and we are going to explain, at least at a high level, what this really means. For now, let's just copy this out and get back to the code and run this and see what we get. So right here, let's say we have random tensor. There we go. We need to specify the shape. So we'll say, let's make a matrix or 2D tensor. So let's say it's 3 by 2. Now you see we have this mean value, standard deviation values, which have been given right here by default, and we're gonna look at what this actually means shortly. The data type is float 32, seed you see is known, name known. Now let's run this, or let's print this out and see what we get. So here we have random tensor, and there we go. As you can see, we have this set of values which are all negatives, and if you notice, they are very close to 0. So here we have practically -1, about -2, -0.3, very small number, and -0.5, -0.87. So these are numbers very close to 7. Let's run this again, so you see that we're able to randomly generate a matrix with this shape with random values. You see that it takes up different numbers. This time around we have a mixture of positive and negative numbers, but again these numbers are very close to 0. Now what if we modify this mean? So we modify this mean, we'll run this again, let's see what we obtain. You see that we have these numbers now, which are instead close to 100. And so what this tells us is that we could make use of this mean and the standard deviation to decide on the kinds of random values we want to have here. Now, to better understand what is going on, let's consider this figure from this probability playground by Adam Cunningham from the University of Buffalo. As you had noticed in the code, when we did TensorFlow random, normal, and the mean, when we specify the mean, the mean is this mu you have here. When we specify the mean to be equal 0, most of the values we had were surrounding 0. And when we set this mean to 100, when we set it to 100, most of the values were surrounding 100. Now, this curve you have here actually explains why. So you have this curve right here, which is bell-shaped. And the idea here is that it permits us randomly pick values around the mean, that's around 0. So that's why you'd notice that at 0, we have the highest probability score. Here, our probability score is f of x. So for values around or values surrounding 0, that's this value surrounding 0, there is much higher probability or chance of them being picked as compared to values far away from 0. So let's pick out these two values. Let's say we have let's say we want to pick out the two values 0.5. Let's say 0.5, and we want to pick out -5. You would see from here that the probability of us having -5 is practically 0. That's almost 0. But the probability of us having 0.5, as you could see from here, if you're taking this middle, the probability of us having 0.5 is about 0.35. Now, if we change this value and take 100, as we did with the code, let's take 100. We have that 100. Well, it looks like they fixed this to 6, so we cannot go above this. We could play around this like this. So you go from -6 to 6. Okay, let's say the mean is 6, so we have the mean of 6. One thing you can notice is that now this 0.5, as you could see, 0.5, let's take this off. 0.5 no longer has a probability of about 0.35 of being picked. 0.5 has a probability now of about 0 of being picked, while -5 also still has a probability of about 0 of being picked. But on the other hand, as you could see here, let's take this off. You see that values like 5 have much higher probability of being picked. 7, 8, 6, they now have much higher probabilities of being picked. Now, this means that if this was 100, or if we're able to get to 100, then it will be values like 97, 98, 99, 100, 101, 102. And this explains why when we ran this code with this mean, we had values surrounding 100. And that's simply because those values surrounding the mean have higher probabilities of being picked. Now let's take this back to 0 and then talk about the standard deviation. So we have the 0. Oh, there we go. You see, get back to 0. And now let's talk about the standard deviation. But before getting into any explanations, let's modify this. Let's say we take 10 here. Okay, it looks like the max is fixed at 2.5. Okay, so let's say we have that 2.5. One thing you can notice is we still have this mean at 0. We still have our mean at 0. That's it. Makes sense because we haven't changed this. But our bell curved shape now appears wider. So an increase in sigma here is what we call the standard deviation. So it's what we called std_dev in the code. So we had the mean and the standard deviation. So sigma is standard deviation. The sigma square is the variance. So sigma square is the variance. Anyway, what we're trying to say here is an increase in sigma will make this curve wider, and a decrease, let's decrease sigma, you see, a decrease in sigma makes the curve thinner and narrower. Now what this implies is that if we have, let's get back to this, if we have sigma square as 2.5, there are much higher chances now that we could randomly select -5 as compared to before. So if this is -5 here, you see there's a slightly higher probability of -5 being picked as compared to when we reduce this. You see, when we reduce this, you see -5 here is practically 0, but when we increase, see, -5 is at least this time around having some negligible value. And so this is essentially the role that the standard deviation plays. Now if we reduce this again, we find that even 0.5, because this is 0.5 around here, even 0.5, let's take this off, even 0.5, which used to have a probability of about 0.35 of occurring, now has almost no chance of being picked. Let's increase that back and set it back to 0. Okay. And so that's it. At this point, we could modify this. We could take this to 6 and then take this to 2.5. And you see that we could take values now between 0, see, we go from 0 to about 11. With that said, we would then look at the uniform distribution, or how to generate random numbers or random values drawn from a uniform distribution. So again, we'll just copy this out and then get back to the code. We'll paste this here. There we go. We have the shape. Let's pick this one. Okay, and then minimum value 0, and now we have maximum value. So you see that unlike here where we had the minimum, the mean and the standard deviation, now we have instead of a minimum value and a maximum value. So let's leave it at this, and then let's say we have random tensor. Okay, so let's print this out. Let's print out our random tensor. There we go. We have random tensor. Let's increase this so we have many more values. 5. Run that. Okay, you see we have this values. Now let's say we change this max value and say it's 80, or let's say 8. Okay, let's say 8. Let's run that. And what you notice now is you have much larger values. Well, values between 0 and 8. But before, the values we were getting were values ranging between 0 and 1. Now this tells us that most probably this maximum value by default is 1. So here you see it's defaults to 1. You could always make use of the documentation whenever you're in doubt. So let's get back here. You see, we'll take this to 100 and then see what we get. You see, we have this values now between 0 and 100. Now the question you may be asking yourself is, what then is the difference between this uniform and this normal distribution? So let's get back again here in our probability playground, and then let's pick out uniform. So there, as you could see, there are many other probability distributions, but we're going to focus on the normal distribution and the uniform distribution. So we get into the uniform distribution, and here's what we get. So we have A and B. Now this is like our mean val, which we saw in the code, and this is like our max val. So when we say mean val -1, max val 1, obviously our values will fall in this range. Now by default, this is 0 and this is 1 on TensorFlow. So that's why you saw the values ranging between 0 and 1. Now as the term goes, it's actually uniform. So this means that all these values here have equal chances or probabilities of being picked. And so unlike the normal distribution where we would have something like this, now we have this square instead, or this rectangle. And so simply here, all we're doing is picking the range of values which we want to have, or which we want to be outputted. So we could get here, increase this. Well, the mean cannot pass the cannot be greater than the max, so that makes sense. Let's reduce this, reduce that. See, from -4 to 4, you see we take all the values. Well, that's it. You see, there we go. We could go from -1 to 2. That's it. Now, one great thing is also the fact that we could modify this and have ints. So let's run this and see what we get. You see, we have only integers now. Now let's say we had known. Let's run that. You see, we have an error. Must specify a max val in the case where the data type is integer. So this actually reading out here in the documentation. So you could see here now that you need to have this max val. So let's change that to, let's say, 1000. See, we'll get values ranging between 0 and 1000. So we have 5 values here from the shape. We could change this, let's say 5 by 5, and then all these values range between 0 and 1000. Another argument which we haven't spoken of so far is this seed argument. And here we're told that this seed argument, when used in combination with TensorFlow random set seed, will be able to create a reproducible sequence of tensors across multiple calls. And so in cases where we want to produce reproducible experiments, we'll want to set this global seed value and also the seed argument value in this uniform, or let's say normal function. So let's go ahead and copy this out. We get back to the code. There we go. Let's just run this right here. Let's take off some parts and print this out. So we print this out. Then we modify the shape and the max values. So we have exactly the same value for the seed here, which is 10. And then here we set this global seed to 5. Let's run this. You see, it outputs 431, 432, 111, and 133. Now let's create another cell. Let's copy this. There we go. Paste this out here. And you see we have the same global seed. And then we have the seed of 10. Now let's run this again. And as you could see, we have exactly the same output as this one. See, 431, 431, 432, 432, 111, 111, and 133. Now, obviously, modifying this and taking, for example, 1 gives us something different. But if you take 10 again, you see you should have exact same output. Now you also see that here, when we take this off, if we take this off and we run this cell, you see we have different outputs. But when we get back here, let's run this again. See, we have another set of different outputs. But when we take this, run that, you see we have exact same output we had already. And now if you want to have more details about certain seeds, you could always check out this the documentation.